Good morning, my dear students. This is again your Virat Kumar, lecturer in Electrical and Electronics Engineering from the Institute of Government Polytechnic, Vattepalli. With the same semester of 4, and the subject is AC machines with the code of 18EE403C. The same topic of alternators. The subtopic for today is EMF equation and problems. So today's main topic is EMF equation and problems. Let us move on. A small recap. So we have learned in the last class about the types of windings, like AC 3-phase single layer wave winding and AC 3-phase single layer lap winding and AC 3-phase double layer lap winding. So these are the things which we have seen in the last class. So today's main objectives are, so on completion of this period you will be able to know, so derive the EMF equation of the alternator, and solve the problems on EMF equation of alternator. So these are the main two topics which we are going to see in this session. Now we'll see the EMF equation of alternator. It's a derivation part. So let us consider Z is equals to number of conductors or coil sides in series per phase. Let us consider Z, the value of Z. Z is equals to number of conductors of coil sides in series per phase. That is equals to 2T, where T is number of coils or turns per phase. So where Z is the number of conductors or coil sides in series per phase, and 2T is where T is the number of coils or turns per phase. One turn of coil has two sides, therefore T is equals to Z by 2. And whereas P is equals to number of poles and frequency F is equals to frequency of induced EMF in heads, and pi is the value of flux per pole in Webers. Let us consider where Z is number of conductors or coil sides in series per phase, and that gives us 2T, where T is number of coils or turns per phase. So therefore T is equals to Z by 2, whereas capital P equals number of poles and small f is frequency of induced EMF in hertz, and pi is also flux per pole in Webers. And in the continuation of EMF equation of alternator, we have already seen that Kd is nothing but a distribution factor, which is given by sine m beta by 2 by m sin beta by 2. This was done in already in the previous class. We have done the derivation part of it and also some solved problems on it. So from that, the value of Kd is nothing but distribution factor, which is given by sine m beta by 2 by m sin beta by 2. Similarly, Kc or Kp, Kc or Kp is pitch factor or cording factor or coil span factor. So pitch factor or coil span factor, that is given by cos alpha by 2. And whereas we know that Kf nothing but form factor that we have learned in the circuits, electrical circuits, which is given by 1.11 if EMF is assumed sinusoidal. If it is a sinusoidal thing, then the value of form factor is 1.11. And whereas capital N is speed of the rotor, which is given in RPM. So moving on to the next slide, the continuation of EMF equation of alternator, we'll just see that in one revolution of the rotor, in one revolution of the rotor, therefore 60 by n seconds, each stator conductor is cut by a flux of pi p Webers. In one revolution of the rotor, therefore 60 by n seconds, each stator conductor is cut by a flux of pi p Webers, where d pi is equals to pi into p and dt is equals to 60 by n seconds. D pi is equals to pi into p and dt is equals to 60 by n seconds. So the average EMF induced per conductor is d pi by dt. The average EMF induced per conductor is d pi by dt. So that EMF is given as E, and the d pi value is pi p and dt value is 60 by n. From this, Moving on to the next slide. So we got that the value of E is equals to pi p by 60 by n. When we just cross multiply, n goes to the numerator. So therefore E is equals to pi p n by 60. And we also know that F is equals to Pn by 120. This also we have seen in the previous classes, that the relationship between poles, frequency and speed. From that we have got F is equals to Pn by 120. From that n is equal to 120 F by P. Now substituting the value of n in the above equation in this, substituting the value of n in this, n value in this, substituting this value in this, we get average EMF per conductor is equals to E is equals to pi P into, substituting the value of n, 120 F by P, see 120 F by 60 by P. That gives us P and P gets cancelled, and 61s are and 62s. Then we get 2 pi F, see here 2 F pi volts. So moving on to the next. So if there are Z number of conductors, in series per phase, then average EMF per phase is equals to 2F by Z volts. 2F by Z volts. And substituting the value of Z, that is equals to 2T, Z is equals to 2T. Then we just get 2 into 2 is 4 F pi and T. So we know that the RMS value of EMF per phase is equals to, multiplying with form factor 1.11 into the above equation 4 F pi T, then we'll get 4.44 F pi T. So this would be the actual value if all the coils in a phase were full pitched and concentrated in one slot. Moving on to the next slide. In the continuation of EMF equation, now here the actual available voltage is reduced due to these two factors. The actual available voltage per phase is equals to 4.44 kc kd pi ft. What is this kc and kd? This is a coil span factor or pitch factor, and this is a distribution factor. So finally, EMF per phase, E phase, is equals to 4.44 kc kd pi ft volts. So this is for phase. And if we just require line, see if the alternator is star connected, we have the line voltage VL is equals to root 3 V phase. VL is equals to root 3 V phase. These conditions also we have seen in the electrical circuits in the polyphase system, that the line voltage VL is equals to root 3 V phase. So moving on to the next slide. So we have finally E phase is equal to 4.44 kpkd by ft volts. So from that we'll see some problems. This problem number 1, a three phase, a three phase 16 pole alternator has a star connected winding with 144 slots. With 144 slots and 10 conductors per slot. The flux per pole is 0.03 Webers sinusoidally distributed, and the speed is 375 rpm. Find the frequency, phase and line voltage. Assume it is a full pitched coils. So this is the question. So we'll see the problem. Coming to the solution, we know that the value formula for frequency is f is equals to Pn by 120, and we have number of poles of 16 into n, a speed of 375 by 120 gives us 50 hertz. That's the frequency. But as they are full pitched coils, Kc is taken as unity, nothing but pitch factor is taken as unity, that means 1, and the pole pitch is equals to n, that is equals to number of slots by pole, that is 144 by 6 is equals to 9. And we know that the value of beta is equals to 180 by n, and 180 by the n is pole pitch, that is 9, so 180 by 9 is 20 degrees, and the value of m is equals to number of slots per poles per phase, number of slots per pole per phase. Then we get number of slots is 144, pole 16, per phase again 3, then that cross multiplies to 16, and finally gets 3 of m. The value of beta is 20 degrees. So the frequency is this. From that we got the value of 50 hertz, and we took the value of Kc is unity since it is full pitched coil, and the pole pitch n is given as 9, and the value of beta got 20 degrees and m value got 3. So from that we just calculate Kd, nothing but distribution factor, that is sine m beta by 2 by m sine beta by 2, sine m beta by 2 by sine m sine beta by 2. So sine m value is 3, beta is 20 by 2, m sine beta by 2 3, m is 3, and beta is 20 by 2, that finally gets 0.966. And z is equals to 144 into 30. 1 second. We have total number of slots of 144. The total number of conductors are given by z, that is 144 into and 1/3, that is 3.33, that gets 480. From that we can calculate the value of t is equals to 480 by 2, that gets 240 per phase. And since it is full pitched coil, the value of Kc is 1, and from that the E phase, directly the formula 4.44 Kc Kd pi Ft. So this is 4.44 is constant, 1 is Kc and 0.96 is Kd. This is pi value 0.03 and this is F by F, this is T, number of turns. So finally we'll be getting 1534 volts. So this is only a value of phase, and in order to get line, we know that EL is equals to root 3 E phase. The root 3 got missed over here. EL is equals to root 3 E phase. Root 3 E phase. If we just multiply with root 3 into 1534, then we'll be getting 2658. So this is the final answer. Okay. So we have learnt about the EMF equation, and we have tried to solve. We have solved one problem in it. So for today's summary is, in this class we have learnt about the derivation of EMF equation of alternator and problems on induced EMF of only one problem, and effects of coding factor and distribution factor. So let us see a small quiz in it. When speed of an alternator is changed from 3600 rpm to 1800 rpm, the generated EMF per phase will become 1/2, twice, or 4 times, or 1/4. When speed of the alternator is changed from 3600 rpm to 1800 rpm, that means it has got reduced to half. Speed got reduced to half, and the generated EMF per phase will become 1/2, or it gets twice, or 4 times, or 1/4. We'll see the answer. It gets twice. When the speed of the alternator is changed from 3600 rpm to 1800 rpm, the generated EMF per phases will become twice. Per phases, the generated EMF per phases will become twice. The another question, the EMF induced in an alternator is given by, he's just asking a simple formula. Is it 4.44 kc kd pi ft or 4 kc kd pi ft, 4 kd ft, none? It's very simple, it is 4.44 kc kd pi ft. Anyone can say it, no doubtedly. Moving on to the next question. One turn of a coil is equal to, one turn of a coil is equal to one coil side, two coil sides, three coil sides, and none. One turn of a coil is equals to one coil side, actually. It's two coil sides. One turn of a coil is equals to two coil sides. Next question. The rotor speed of an alternator is n rpm. Then the time taken to complete one revolution is 60 by n seconds, n by 60, 60 into n, and none. It's obviously 60 by n. Let us see. The rotor speed of an alternator is n rpm. Then the time taken to complete one revolution is n by 60 actually. 60 by n. We'll just see. 60 by n only is right. Okay, that's it for this, I think. So there are some frequently asked questions in this, like derive the EMF equation of an alternator. And there is a problem over here that find the no load phase, and line voltage of a star connected 3-phase 6-pole alternator which runs at 1200 rpm, having flux per pole of 0.1 Weber sinusoidally distributed, and its stator has 54 slots having double layer winding, and each coil has 8 turns. The coil is corded by one slot. That means it is not a full pitched coil. The coil is corded by one slot. Try to solve this problem in the next class. There are some more problems also, that a three-phase 10-pole star connector alternator runs at 600 rpm, and it has 120 stator slots with 8 conductors per slot, and the conductor of each phase are connected in series. Determine the phase and line EMFs if the flux per pole is 56 milliwebers, and assume full pitch coils. And there is another problem also, like a 4-pole 3-phase star connected alternator armature has 12 slots with 24 conductors per slot, and flux per pole is 0.1 Weber sinusoidally distributed. and calculate the line EMF generated at 50 Hz. There are also some more questions that a 3-phase 16-pole alternator has a star connected winding of 144 slots and 10 conductors per slot. The flux per pole is 30 milliwebers sinusoidally distributed. Now find the frequency, the phase and line voltage if the speed is 375 rpm. And there is another problem also, like a 3-phase 10-pole alternator has 90 slots, each containing 12 conductors if the speed is 600 rpm and flux per pole is 0.1 webers. Calculate the line EMF when the phases are star connected, delta connected, and assuming the winding factor to be 0.96 and the flux is sinusoidally distributed. So that's it for the today's session. So thank you one and all.